Hi there, it's Ian McTavish from Team 4152, and this is the 7th in our series of tutorial videos for our Techno Girls MiniBot project. And this one focuses on motors and gears. Again, we can't do these kinds of tutorials without the sponsors that we have, and really want to appreciate all the help that we get from them. And the overall goal for these tutorials is to design a MiniBot, and we've got a series of girls from grades 5 to 10 that are involved in this, and we're doing it remotely because of COVID-19. And our goal today is just to learn about the motors and gears and select them from our robot. So just a little bit of background. Motors that we use on a robot are electric, and if you took apart an electric motor, you would see that there's magnets, and basically an electric current runs through the wires, which magnetizes the wires. So if you have a positive magnet and you're pushing it against another positive magnet, you're going to get repulsion, where the magnets move apart. So that's the basic idea with how the motor works. There's a couple key terms that are really important. Free speed, so this we measure in revolutions per minute. So if the motor was just running with the whatever amount of voltage you're doing, what speed is that shaft going to be turning at? So if you were to count, it went this many turns over the course of 1 minute, that's how fast it is. You can use that information if you know the diameter of a wheel to determine how fast the wheel would turn and how much distance that the motor would cover. The stall torque, so this is how much force. So if I've got a shaft turning and I apply a force against it, how much before it stops? If you're thinking, if you're biking up a hill, you might reach a point where you just simply cannot pedal anymore because the amount of gravitational force is preventing you from getting up that hill. So typically with motors, we measure it in ounces per inch or newtons per meter. So if your shaft was turning a pulley that was lifting a weight, you could determine exactly how much weight you could use before the motor would stop. And if a motor stalls, the electrical current is going to go up when it stalls. And so this is how much electrical current is going to be going through when that motor stalls. And this is a really important thing, because if increased current will increase the level of heat. And so you can get a point where a motor is trying to push and it simply can't. So the current goes up, the wires get really hot, and when things get hot, things start melting, and then you get fire. So if you know the stall current, then you know what fuse to put on so that it will pop the breaker or blow the fuse before it damages the motor. That's typically measured in amps. The website listed there is a really good resource to learn more in detail about this. So when we go into competition, we are following the rules for the FIRST robotics competition. So the rules, firstinspires.org is the website, and it's really important to spend some time exploring it so that you know how to pull up the manual. So this is from the manual, and you can see that it lists the types of motors that we're allowed to use on our robot. So this is really important. You basically don't use a motor unless it's listed in the rules. And in terms of motor specs, in the firstinspires.org website, if you go to the FIRST robotics section in the programs, you'll see that there's a lot of different resources. And there is a chart like this, which is really handy because it gives you information about the different motors and how much power they can have. Now this is from 2017, so it's missing some of the newer motors. And when you're looking at newer motors, typically go to the manufacturer's or the seller's website, because they'll have the detail. So Vex Robotics is a good example. In Vex Robotics Pro, they sell a lot of different motors, and this, for example, is the MiniSim motor. And this is what we're using on the MiniBot, and I'll go over a few details about it. So those values that we were looking at before, Vex does a great job of putting all those values into a nice graphic, which makes it easier to understand. So for example, this is their speed along the top, so that you can see with this yellow line, my yellow line is my torque. So this is how much force. So it's 1.41 newtons per meter. So I can see that my stall torque is 1.41. So here's 1.4. All right. So when the motor's not just starting running, that's basically my torque. And basically, the faster the motor runs, you see, the less torque there is. And this is an important concept with all motors. Basically, if it's really fast, it doesn't have as much torque, and if it's going slower, it has a lot more torque. There's also the peak power. So I can see at 250 watts, that's my peak power. So that's kind of my best bang for the buck at that point. So that's about 2,920 revolutions per minute. So I can see that that's probably where I want to be looking at. And I can use these other graphs to get an idea of how efficient my motor is and all of that. So there's a lot of information in here. Now, the problem is that usually your motors you don't want to typically run them without being able to change their speed or their torque. And this is where gears come in. So you have a 10-tooth gear right here. So let's say that's attached to the motor, and you've got this bigger tooth gear here. So this one has 50 teeth. So basically, as this small one turns, and I'm just going to put on my thing. So as this turns, each tooth is going to engage, and it's going to turn another one. So this will go all the way around. But what will happen is that will only move this 10 teeth. So this has to go 5 times around before this will go once. So you can see if I've attached this small one to a motor, the motor can go really fast, and the output from this gear will be much slower. It'll be 5 times as slow. So this is really useful concept because I can change my speed. So now my output is maybe 584 revolutions per minute. So it's slower, but it also increases my amount of torque. So now I'm going to get 3.5 newtons per meter torque out of this. And with my calculations, I'm just basically dividing by the gear ratio or multiplying for the torque. It's not quite that simple, but for our explanation, it is. Now, the JVN calculator, this is a really useful tool that somebody created, and there's a link that you can download it. It's a spreadsheet, and you can upload the spreadsheet to Google Sheets, and so that you can actually make changes in it. So on the spreadsheet, there's a whole bunch of different tabs, and this is the tab for the one-speed drivetrain. And basically what you can do here is you can put in what motor you want. So this little drop down, I can pick the different motors that are available. And with the red, I typically will look at these. So for example, number of gearboxes and drivetrains, so we're going to have 1 on each side, so 2 in total. And we're going to put 1 motor in each gearbox. The total weight of our robot, I'm estimating, is going to be 25 pounds. So our MiniBot is much smaller. Typically, FRC robot can be about 150 pounds. They're fairly big. And then I can also decide what size wheels. So I'm just going to aim for 4-inch wheels. Then in here, I can start playing around with the gears. So I go to the Vex Robotics website and I look at the different gears and stuff. And I am using a 14-tooth gear on my motor. And how I picked these is basically I looked through what gears we currently had, and these are ones that I have available, so I'm just going to plug them in. So if I'm going from 14 teeth and driving 50 teeth, then 16 teeth to 48, and then a series of sprockets 12 to 15, this will give me a gear ratio of 13.39 to 1. And basically that's going to give me a drive speed of about 7.61 feet per second. So that's kind of I did some tests of, okay, if I'm covering this far, and I think that's a decent speed. It should be fairly easy to manage. It's not terribly fast. In competition, we try to go much faster than that, but if we're in a situation where we're going to need to push other robots, then this is really good speed. And this is the free speed, so in reality it's probably going to be closer to 6.16 feet per second. And the other thing is that it's going to draw about 18.72 amps per motor. So I can reduce that by adding more motors, but basically by changing the gears, you can see what kind of speed you're getting at. So you can play with different numbers here, and when you find a ratio that gets a nice speed and a nice amps, that's perfect. So with our drivetrain motors, usually we're on a 40 amp circuit, so we want to keep this number under 40, and under 20 is fabulous. It's nice and low. I've got a little bit of wiggle room, but you want to play with the numbers to find the ratios that are going to work, and then you can figure out what types of gears you need to buy to make your robot work. So, motor pinions. So the first gear is a motor pinion, and this is an example of one of them, and it fits directly on the shaft of a mini-sim motor. So a mini-sim motor has a round shaft that's got a little slot, and you can see the slot here. Basically, this slot allows you to put a key stock on it, and the key stock is just a rectangular piece of metal, and that will go in here and it will slide into the shaft of the motor, so that it kind of locks it in place, so that as this turns, as the motor shaft turns, this will turn as well. And the different types of motors you have are going to use different types of pinions, so it's important to make sure that you're getting the right pinion for the right type of motor. So gear 1 is the 14-tooth gear, and in Vex Robotics website, that's the particular one that we're going to be using. Now, if on the Vex Robotics website, down at the bottom of the MiniSim page, you can see there's a whole bunch of different options, and the drawings are one of them. And this is the drawing for the 14-tooth gear. You can see the tooth count, and you can see the pitch diameter. So, in order to plan our gearbox, we need to know the pitch diameter, and there's a nice little trick here. We have a 14-tooth gear, and our gears are 20 DP gears. That's the type of gear they are. And this DP stands for diametrical pitch, but basically, if we take 14 and divide it by 20, we get 0.7, and you'll see that is the pitch diameter. So that is the diameter of this line. And basically, when we're designing our gearbox, if this line is touching another circle with the same thing, then we know that the teeth are going to engage. So we got to make sure our gears have the same diametrical pitch, and then we can line up these circles so that we know that the teeth are going to line up perfectly. So our 14-teeth gear is, if we were to get this overall gear ratio, then we would need a second gear of 187, which is going to be 9 inches in diameter, not going to work very well. So this is how we do stages. So our 14-tooth gear is going to drive a 50-tooth gear. Then what's going to happen is we're going to put a gear on top of the 50-tooth gear that's going to drive a 48-tooth gear. And so that we're going to have multiple stages, which will allow us to get the gear ratio we want without having a ridiculously large gear that just simply won't fit. So gear 1 drives gear 2, gear 3 is on the same shaft as gear 2, and it drives gear 4. And then we're going to use sprockets, and we're going to cover those in a later tutorial. So gears 2 and 3, they're going to be on a 3/8 inch hex shaft. And the hex shaft is really nice because you can just slide the gear onto it, and when the hex shaft turns, because it's a hexagon shape, the gear will automatically turn. So it's very easy to mount them and assemble them. So gear 2 is our 50-tooth, and gear 3 is our 16-tooth. So there's the information for that. We have the pitch diameter, but again, 16 divided by 20 dp gives us 0.8. 50 divided by 20 gives us 2.5. So we can calculate those. Gear 4, there's gear 4, and it's a 48 tooth, and again 20 dp, it's going to be this. Now this is going to be our output, and we're going to use a 1/2 inch hex bore for this. So a 1/2 inch hex shaft is what our wheels, how they are designed, so it's going to be easier to use the same thing with the gear. So that's our goal. Now, gears are one way to transfer force from a motor. There's other ways, so chain and sprockets are a way, and if you think of a bicycle, most bikes use a chain with a sprocket type system. There's also belts, and for example, on our lawnmower, I've turned it over and had a look, and there was belts that took the power from the engine and transferred it to the blades. So chains and sprockets, belts and pulleys, there's different ways to attach things. With the gears option, there are some ways. So Vex Robotics sells something called a versaplanetary gearbox. And if you think about a drill has a very similar type of gearbox attached to it. And that allows you to attach a gear system in a very small space. So that can be a very handy thing. Being able to buy that type of gearbox makes it really handy. Gears do need to be greased, and they can be pretty noisy. And the other thing is, when you're manufacturing, you need to be incredibly precise to line gears up. You don't want the teeth to be too close, which is going to cause them to bind up, or too far away where they're going to not fully engage, and the wear and tear on them can prevent them from actually touching. Multiple stages allow you to get really good gear reductions, and there is a center-to-center distance calculator that you can use on the web to be able to do that. And all of these links are in the slideshow and can be clicked on and go right to them. Chain and sprocket they're pretty noisy. Now the bonus with the chain and sprocket is that I can change how long my chain is. I can break a link or add more links to it, and so I can take my chain and make it longer or shorter. And that can be really handy as I'm prototyping and trying to design something, and I'm not going to worry too much about how far apart they are because I can just modify my chain. Now, chain can stretch over time, and that I'm using the word stretch. It's not technically what's happening, but basically, as chain gets used over time, the stretching friction wears away some of the pieces, so they pull apart. Well, if you're only pulling apart a fraction of a millimeter, it doesn't seem much, but when you have maybe 100 links, that can add up to quite a distance, and that can change your tension on your chain. So that's something that you have to keep in mind. Now with sprockets, you can manufacture them fairly easily, so there are some bonuses. If you wanted to make a turret, for example, you could use a chain and sprocket, because then you can laser cut the plastic to make a sprocket. And there's some links to calculate how many links for different distances and how to break and assemble chain. Belts and pulley. Belts are pretty quiet, which is nice, and they don't tend to stretch. We really like using belts, and we've got some really tiny belts and pulleys that can allow us to transfer the power from a motor into a really kind of tight space, which is nice. You do need to be incredibly precise with your center-to-center distances, and there is a calculator online that you can go to. West Coast Products has an excellent calculator. And this allows you to have your motor farther away. So with the gearbox, the motor and the gears are very close together. Belts and chain, you can set different distances away. So our sprockets, we buy them from Vex Robotics as well. And the 12-tooth sprocket is there, and they're a 1/2 inch hex, and then our 15-tooth is there. And so that's our sprockets. So just a quick summary for our MiniBot. We're going to have 20 DP gears. Stage 1 is a 14-tooth sim mount pinion, and it turns a 50-tooth 3/8-inch hex bore gear. Stage 2 is on the 3/8, and gear 3 is, and it's 16-tooth, and it's turning a 48-tooth gear that is on a 1/2-inch hex. And then attached to that same hex is going to be our sprocket number 5, which is going to be 12-tooth, and it's going to be turning a 1/2-inch hex that is attached to the wheel, which is a 15-tooth. Hope you've enjoyed this and learned a few things, and have a great day.